All right. So what is a sequence?
It's like a bunch of numbers.
Okay, a pattern of numbers. I like that description. A pattern of numbers. And we can actually describe it as a function whose domain is the set of positive integers. We plug in 1, then we plug in 2, then we plug in 3, then we plug in 4. So we don't have like a continuous curve. If we were to look at a graph, we just have dots because our domain is only positive integers. Okay. Also remember that when we notate them, we typically see them notated with n's, sometimes k's, but we use this notation. This is going to be the more popular of the notation, a sub n, right? If we have a sequence, sometimes we'll write it like this also, but n or sometimes k will be the variable that we're going to use. We would not be using x. Okay? So, some sequences.
He's just my thing now.
What?
Stop.
All right, what is can anyone tell me what the sequence is?
1, 2, 4, 8, 16.
Okay, and if we were trying to write a rule for it,
2 to the n minus 1.
Yeah.
Oh.
Quite very.
because if we plug in 1, we get 2 to the 0. If we plug in 2, we get 2 to the what?
0 to the negative 1, so it'd be like 1 positive. I just messed that up. Oh.
Domain is the positive integer.
We have to start at 1.
Yes. Okay. What about this sequence? 1/2, 2/3, 3/4, 4/5, 5, 6, 6, 7.
And n over 1.
Huh? Okay, what? Isn't it just add like 1 to the top and 1 to the bottom?
Yeah. And
So n. And then 1 more down.
Why can't you just like say, dude, add 1 to the top and add 1 to the bottom? Why is
I
that
feel like
so
that's more
complicated?
work than saying n
Or
over
like
n
the
plus
top
1.
one, why can't you just say multiply it by 2?
Well,
Does it have
you
to
can
be
use
2?
words, but we're going to have to use descriptors in a function sense in order to do what we need to do. Okay.
Which part?
Let's go down to this one right here.
The alternative.
Yeah.
Negative 1 to the n.
Minus plus 1.
Neither one would work.
Okay. Well, only one is correct in this case. Either one will work if you want alternating signs, but if you want to start with a positive, we need -1 to a power to end up being positive, so we would need the n plus 1. If your first term is negative, -1 to the n would get you that -1 first.
I was talking about plus
N
or
minus
minus.
1.
N minus 1.
Oh,
I was talking about plus or minus.
okay, I'm with you. You are right. N plus 1, n minus 1, either one would be fine.
I choose to just do 7, just because of it. You wouldn't mind that.
What?
Nothing. He said nothing. All right.
Like just add 7 instead of
The limit of a sequence.
I'm doing that.
The limit of a sequence.
Movie man.
Did we learn this?
No. Did you ever talk about sequences last year in Calc BC?
Possibly. Pre-calc, though, we did.
But
Did
did
you
you
learn
know
about
about
limits?
limits in pre-calc?
No.
Okay, then no, we have not done this before.
Read it.
What am I supposed to write now? Why is there like brackets around the
I think it's like
Wow, I have a lot of calculators.
Oh yeah, I'm
That's
charging
good.
right now.
You are? Okay.
That's a pretty arrangement.
as L
I think I have some of my third hour kids must be charging theirs also.
Oops. Wait, lima beans? Where'd you get the beans?
Nowhere. It just looks
Lima.
Oh.
Oh wait, now I.
Did you see the
okay.
post?
Why is there a capital L on both sides?
I'll show you this. You want to take a picture?
No, but my brother was. Oh,
You
oh,
should.
and
Yeah,
it was the line. It was the line. Yeah.
I was not sure if this is like a special limit, so. Yes.
My brother was like,
Yeah.
oh, the fashion, the red carpet was so
I
amazing.
just realized that.
All right, I guess we're done writing this down. Okay, now, if we have a limit, then we say that our sequence converges. If we don't have a limit, then the sequence diverges.
What if the limit goes to infinity? It still diverges even though that has a limit? Because it's going some.
Say that again.
Like, what if it's going to infinity?
Then that limit doesn't exist. An infinite limit is a non-existent limit. We just describe it as infinity.
Never mind. Stop about. I'm sorry, but 0 times infinity is 0. It's just.
In some
That's
cases.
just how it works. It's just not.
In what case could it possibly be?
Okay. Now, I don't think you need to write all of this down, but what I want you to understand from Theorem 8.1 is that if we take a function, like if we take a sequence and we write it as a function, whatever limit we take of that function, well, that would also be the limit of our sequence. So basically, think about your limit rules from Unit 1 last year, and we can apply them to our sequences. Okay? Because they just have a more limited domain. That's the only difference.
Limit.
Yes.
I don't get it. What does theorem 8.1 say?
Okay. We have a sequence, and f of x is basically describing the sequence as a function in terms of x. Whatever the limit is towards infinity of our function, we can then apply that, and that would also be the limit for our sequence. Basically, you can take the limit of a sequence the same way you take the limit of a function. That's what it's saying. Is that clearer for you? Okay. So, this sequence that we talked about earlier, we decided it was n over n plus 1. So if we take the limit as n approaches infinity of said sequence, what do we get?
Oh, you just plug it
With a few extra steps.
You can either think about
What?
you can either think about L'Hopital's rule
in. Oh.
with infinity over infinity,
Okay.
or that our horizontal asymptote is at y equals 1. Either way, we get a limit of 1. And so what we can determine is that this sequence converges to 1.
So we won't get counted off points if we don't do the 0 over 0 or infinity over infinity. Check mark. You know what I mean?
In
Like,
this case, I think it's simple enough to where you could do it in your head.
But you're supposed to still show your work with that, but you know that we.
We're only in slide 3.
Okay. Let's write the rule for this one. 1, 1/3, 1/9, 1/27, 1/81st. What sort of numbers are in the denominator? Powers of 3, but we start with a denominator of 1.
Yeah.
So 3 to the n won't suffice. 3 to the n minus 1 would need to be our denominator.
I know.
What did you say, Zane?
Oh, remembering.
You're going to be fine. I meant to pick up the The limit as n approaches infinity of 1 over 3 to the n minus 1 would be what?
0.
So this sequence converges. Excuse me. This sequence converges to 0.
So if it didn't have a limit, it'd be divergence.
Yes.
How is there like a
That's
limit
the
of a
divergence.
sequence though? If it's just numbers. Isn't that just like a line?
As this continues to grow, like as we go through the domain, our outputs get closer and closer to 0.
Okay.
Because this is an infinite sequence as our domain goes to infinity. Okay. Now, the converse of the theorem is not true. And you don't necessarily have to write this down. Let's just talk about it. Okay. Here I have this sequence. This sequence has a limit that does not exist.
Function does.
Well, it's more about the converging part. Okay. Plug in 1, what do you get?
Oh boy.
With this 1 plus the sine of pi.
Okay. Plug in 2.
1/2.
Plug in 3.
That's 1/3.
Does this converge?
Is there an easier way to do it?
Looks like it does.
I feel like there's an easier way to write it.
There is. Okay. So what this is saying, so if our limit is a value, then we converge to that. Okay. But if, what am I trying to say? Let's go back to the written here. Like I had it all in my head ready to go, and then,
Absolutely.
I know. Okay. Okay, just here, this is what I was going to say. Just because the sequence converges doesn't mean the limit exists. Like, you can't go backwards.
So there's no limit.
I'm
Okay.
confused. It said, you said converges, but that says it doesn't exist.
The limit doesn't exist.
So,
But that's what we were
So
So
you-
we
how
were
would
finding
you-
the limit, and that was where we were converging. But now,
But
we don't have a
but
limit.
if we look at this as n, 1 over n, then that sequence can converge. It's the,
so because sine
so we need to
is
focus
always-
on these numbers.
the second part's always 0. It's like converges. Forget about it.
Okay, let's talk about rules for limits. I don't think you need to write this down. I think we just need to remember them. And we're just going to apply them to our sequence situations. Remember, if you have a constant, you can throw it outside of the limit. Okay? Remember that if you're adding or subtracting inside of your limit, you can break that apart. Right? Like, I'm not changing your life by any means right here. Okay. If we're multiplying inside of our limit, we can break that apart and do each limit separately and multiply them as long as we don't get an indeterminate form, and then we'll have to go with a different story, right? And if we're dividing inside of our limits, we can do those separately. Okay?
Provided that the denominator is not equal to 0.
Yep, that. Now, we only say that's not special. We only say that the sequence converges if it gets closer and closer to a real number. So let's just get some vocabulary straightened out. We never say a sequence converges to infinity. That does not make sense. We instead would say that it diverges.
To infinity.
You can just say diverges. You wouldn't have to say to infinity.
What if it goes to negative?
Diverges. It is a divergent sequence. Okay. A sequence doesn't have to go to infinity in order to diverge. Like this sequence right here diverges. Because- Yeah, there's no limit. Okay, it's not approaching a certain number. It's just bouncing between two values.
But okay. Come on.
Ask your question.
Well, the other one was like oscillating too, but it converged. But it didn't have a
No,
limit.
it didn't. It just kept getting smaller.
Which one oscillated?
You're talking
what?
about 1 over n.
Never mind, I was thinking-
pi n.
Never
We
mind.
should go back to that.
It-
1 over
I
n
was
plus
thinking
sine of pi n.
sine.
Technically,
Never
it goes. Technically, it
Right,
oscillates.
Right, so like sine of pi n.
But it's all.
Yeah, that's
for,
hard.
for
Pi over
sequences.
2n.
For sequences, it's you only work with the integers, not all the numbers. The integers were converging to 0. The graph itself was oscillating.
But if this were like, we can still oscillate and converge as long as we're oscillating to a value. So bear with me. Like, if we go from
So if the oscillation between
1, -1, or like 1, -7/8, +3/4, negative. Do you see what I mean? Like if we
And it
can
gets
oscillate but
sine
keep
of
get
n
closer and
approaching
closer.
0 from the
It's like a wave that
Sine
starts
of-
off with a big
Sine of sine of
Like
n over
this.
sine of n over n starts goes big in the middle and goes small as you go out.
All right, we need to talk about the word monotonic. You've heard it before, but you probably forgot about it.
It's like a polyatomic. I don't know.
Isn't mono mean
One type of tonic.
Yeah.
Monotonic means non-decreasing or non-increasing.
Let me the word of origin.
Are we supposed to leave the space?
Well, if I'm talking about non-decreasing, then the second term is greater than or equal to the first term, etc., etc., etc.
And it's or not in, so it can't. So
Wait.
it's
So
non-decreasing
by-
or non-increasing.
Oh my
so it's just increasing or equal to.
So it's not- So it's just like it could be just increasing.
Yes.
So it's just a weird way of saying it's increasing. It's a non-decreasing.
Or
or
equal.
it's equal all the way?
Okay.
So if it was equal, it'd be not decreasing.
But like I have seen a sequence who the first term and the second term are the same.
Yeah,
But then they start to either increase or decrease.
like Fibonacci.
Yes, like the Fibonacci
Like the
sequence.
bear.
Like the bear.
Thank you.
Ugh.
Did you realize that Connor's last name just had that to it? Yeah, I realized that.
He's related.
All right. A bounded sequence. In your words, what do you think it means to be bounded?
A
To be tied down.
Definite starting and ending point.
Okay.
I'm going with that and I'm sticking with it.
So if we're bounded from above, then every term is less than or equal to some number. Every term is less than or equal to a number. If we are bounded below,
It's great.
okay, and it is possible to be bounded on both ends.
I was right. Keep it down, man.
Okay,
You
You're bounded above, all of your terms are less than or equal to a number. If you're bounded below, all of your terms are greater than or equal to some number.
Okay, that makes sense.
Okay? Does this make sense? If our sequence is monotonic and bounded, then it converges. Monotonic, non-increasing, non-decreasing.
That just means it's not like.
Yeah, and so like they could go
It's
to
just into
Right. It's not oscillating.
not oscillate, that's okay.
so it can go to infinity, but like if you test it for it goes monotonic. Downward then.
So it would just be like if it
Say your question.
So like if we do the one that and it diverges, but then we do the monotonic and bounded, then it could be convergent.
would just be the end of it.
So the limit is going to give us. The limit's going to give us the bounded. Well, no, not necessarily. The limit's going to give us what it converges to. I see what you're asking. Yeah, if we can show it's monotonic and bounded, then it's converging.
Do we bound it or is like
Yeah.
it's bounded?
I could determine the
Like
number
to-
to bound it.
Ask that again?
Like will the book say where it's bounded?
Like, how would we determine the
Can you just bound it
upper
wherever you
seven
want,
at-
and it converges?
Really? 'Cause we
Well,
like
like,
two
I
numbers.
think we could all, like, if we go to this sequence right here.
Oh, it's bounded below the one.
bounded. Well, it's not just across here. So it's just a
It's
limit?
bounded below by 0, right?
So it's just a
Bounded
limit?
above by 1,000.
Like, this is bounded by 0.
Yeah.
Okay.
So it's just a limit?
I don't want you to get too hung up on the bounded because that's probably the more, like, it will be obvious what it's bounded by, okay? The monotonic is what I want to work on, okay? Don't write this down. Let's just kind of talk about it, okay? If we have an increasing, then A sub n is always less than the next term, right? And if we're decreasing, A sub n is always bigger than the next term, right?
Yep.
And then if we relate that to non-increasing and non-decreasing, then we have the equality there. Okay? Take that in for a moment. Does that make sense?
No,
Why?
because I feel like if something's increasing, wouldn't it go like 1, 2, 3, 4, 5? If that was a thing, wouldn't that mean because like the numbers are getting bigger as you go along? But that seems to say like not that.
So my first term is smaller than my second term.
Yes.
Isn't that what you just described?
No.
Yes.
Yeah.
1, 2,
Wait,
3, 4,
oh.
5?
I'm sorry,
Right?
I got this backwards.
Okay.
Yeah.
Okay, I'm just double checking.
I'll get him out.
So what we're going to end our time with today, there are 3 ways for us to show that a sequence is either increasing or decreasing. Okay? So let's take these right here and let's think about them in a couple different ways. So we have what's called a difference test. Okay? If I subtract the 2 terms, can I tell if we're increasing or decreasing?
Yes.
Yes.
Okay. Oh, why did it get all crazy here? I'm gonna fix the formatting. We can tell if our sequence is increasing if a term minus the term before is greater than 0. versus, and I don't know if you really want to write this down, but I think we can infer without writing it down that, oh, I guess I have it down. The ways that decreasing would just flip that sign. Okay.
Cool.
What about the ratio? If we had an increasing sequence, what would be true about the ratio of a term over the term before it? If we were increasing.
Well, greater than 1.
There we go. It'd be greater than 1.
So it's not. Why do we need multiple of these?
Because maybe I don't want to subtract. Maybe I want to divide.
Just because.
I feel like there are sequences that I wouldn't mind dividing and would really not want to subtract terms from. And we're talking about like in general, like a sub n plus 1 divided by a sub n. I'm not talking about a sub 5 over a sub 4. I'm talking about in general, we're using n's. Okay? Like we have to make it true for all of the sequence, not just from term 4 to 5. Okay? And then what will probably be your favorite? What's another way to determine if something is increasing?
It's not increasing.
The derivative. If our derivative is always positive, we know that we have an increasing, in this case, sequence. And for the other two, we would have to find the difference and we would have to find the ratio. Okay, we have to do work for all of these. Okay, still 15 minutes. I don't know if you need to write down the other part of each of those, but if we just flip the sign on each of them, we have the decreasing rule. Okay, but I feel like that's intuitive a little bit, maybe. Okay. So I'd like to show you how to use each one of them. Or maybe just, yep, each one of them. If we have time. We have 15 minutes, which this is going faster than I thought. Thought you'd have more questions. So let's get to it. Are we ready? No? Chris is not? Chris is ready. Okay, write down this sequence.
On the quiz, will you have us do the difference ratio and derivative test? Like, will you specifically ask us to do it? Like you did with this question?
That's a good question that I'm not sure I can answer at this time. So you may have to decide which one is best, and you may have to do one based on my suggestion.
Okay, what if this, because like in order to figure this out, you would have to, I think, use one of the tests and like pick 2 random numbers, right?
Nope.
Nope.
We have to keep it in terms of n.
And
So,
numbers are gonna do this.
If we're going to do the difference test, Benjamin, we're going to literally take a sub n plus 1 and subtract a sub n.
Oh, that is
And
right.
compare it to 0. So a sub n plus 1 would be n plus 1 over n plus 2. And a sub n is n over n plus 1. We are literally going to subtract these. How do we subtract fractions?
I don't know. Couldn't tell you. It's taking up almost an entire page of my which is weird.
I swear questions
Okay, so we have to make common denominators. Look at this. What happens when we subtract our numerators?
Don't know.
our difference test, we are basically seeing, is the difference positive or is the difference negative? In this case, it is very obvious. Like, we don't have to do any proving of anything. We know that this is always going to be a positive number. So if the difference between the n plus 1 term and the n term is positive, then we know that this sequence is
Increasing, non-decreasing.
we can say increasing.
Increase.
That's always going to be above 0. Yeah. It's never going to be equal to.
Is it also non-decreasing?
Yeah. More specifically, it is increasing. But you could also describe it as non-decreasing, which we might find annoying. But
Is n always going to be positive?
n is always going to be positive because we're talking about a domain of positive integers. Okay. All right. Let's try the ratio test on this same sequence. Yes.
So would it ever be where it would be a non-increasing? Like you would solve it and you get a non-increasing? Or is it always?
With these tests, it's going to be either increasing or decreasing. Okay, so for our ratio test, we want to determine what the ratio of a sub n plus 1 to a sub n is. Okay, so we're taking n plus 1 over n plus 2 over n over n plus 1. What did you just say? What did Zane say? Did I hear copied up flip?
Yep. No. Who said that?
Same, why'd you say that?
Oh.
But that's like how we do it.
Yeah, no.
Well, I
I
thought
know. I just don't like that phrase.
Nobody said that.
Multiply
Copied up.
by the reciprocal.
What is copied up? What?
Nothing. I'm
The
not.
reciprocal.
You flip it and there's a dot.
What's wrong with that? Isn't that how you do it?
It's catchy.
It
That's
is
how you do it.
Okay. Here's what we get
Yep.
when we actually perform the division. We have n squared plus 2n plus 1 all over n squared plus 2n. When we are using the ratio test, we want it to be clear to us whether it's greater than or less than 1.
Great. Wait.
Is it obvious? It is very obvious that this fraction is greater than 1 because the numerator is always, without any proving, greater than the denominator. It is literally one more. It
By
will
one.
always be greater. Yes. So we know, and we knew from before, but we know that this is an increasing sequence.
What to the
We have one more test. What's our other test?
derivative.
It might be easy.
I have no more slides. No.
Was this it? Input over input?
That's what
Okay.
I'm talking about.
So our derivative test, we would basically take the derivative with respect to n. Using quotient rule.
What's that?
It's not funny.
It's like product rule, but different.
Who know about this?
Always.
It's always going to be positive. And if our derivative is always positive, then we know that our function, or in this case our sequence, is increasing always. Okay? This will sporadically
Brain break.
come back. Okay? You have a book assignment. tomorrow we are gonna start looking at our infinite series. Okay.
Oh.
We will learn a plethora of infinite series tests for convergence. What's wrong?
It's a lot of problems. 29 to 59.
All?
That's still.
And then 17 to 23.
And they're not bolded.
That's 30.
They're not bolded. Can you use odds only for everyone except for
15 plus 3 plus 4 plus 3 plus 7.
And we ended.
that.
I know.
That sounded like a lot.
That's a